Hi folks, welcome back. It's me, Mr. Hess again, ready to teach you another section of chapter 7. In this chapter, we're going to skip section 5, so we're going to jump to section 6. In section 6, the title of this section is Fractals and Self-Similarity. I think you're going to kind of like this section, especially if you like neat patterns and if you're artistic. A lot of that applies here. A fractal is when we can create a shape after repeating the same steps over and over and over again. In fact, every time we repeat the steps, it's called a stage. So if you look at a picture of a fractal I've made up here, stage 1 looks like just this V shape here. In stage 2, you'll notice at the end of the V here, they split the ends of it at each end. So that is now stage 2. Okay, and they're going to repeat those steps. They're going to keep doing that. So now they've got 1, 2, 3, 4 ends here that all get split again, thus creating stage 3. And a fractal, you can theoretically do this forever. You could keep repeating the steps over and over and over again, and the shape would continue to grow. And in this case, this would keep spreading out. In fact, this one kind of looks like a tournament bracket, you might say. Like in March Madness or something, you have teams playing each other and keep playing each other till eventually you get down to the champion. But a tournament bracket then is a type of fractal. Because it does have a process that's repeated over and over again to produce that shape, that tournament bracket. Now we mentioned that fractals have what we call self-similarity. That's why they're in this chapter, in fact, because remember this chapter has been all about similar polygons. And fractals are unique in the fact that they have self-similarity, meaning that, for example, if I break off a piece of this fractal, maybe if I were to focus on this spot right here, if you were to take this and blow it up a little bit, okay, you would get the exact same picture of stage 2. See it there? Where it splits and splits again, splits and splits again. See, stage 2. It's just a smaller version of it, so it's similar to itself, similar to a previous stage. Okay, you should be able to do that with any fractal. You should be able to break off a piece of the fractal, zoom in on that part, and find that it's really identical to the original fractal. It kind of reminds me of, I don't know if you've ever seen them do this on TV before, but a TV camera will shoot a picture of the camera itself on a screen. So then you see a picture of the camera and a picture of the camera and a picture of the camera, and it keeps just like shrinking smaller and smaller and smaller. So these are kind of trippy. These are kind of mess with your head. Some of these things do. Okay, but since they have self-similarity, that's why they're in this chapter. Okay, let's take a look again at some more fractals here. And every fractal, those stages I mentioned, those stages are determined by what's called an iteration process. So every fractal has a set of steps that you follow to create the fractal. Okay, and those steps that you follow is called the iteration process. It makes sense if you think about the name, because to iterate, if you know what that word means, to iterate means to repeat. If I said there's a test tomorrow, I iterate, there's a test tomorrow. You're repeating it for emphasis there. So to iterate means to repeat. So an iteration process is a set of steps that we're going to do not just once, but then we're going to go through and repeat them again and again and again. Okay, so when we do these problems, then they should also specify what stage they want you to go to. Okay, so for example, on this fractal, here's the iteration. Here's the iteration process, and let's say that I told you to draw a stage 3 of this. Okay, so the first thing that I would do, if I follow my steps here, I'm going to draw a square. Okay, next step, attach the hypotenuse of an isosceles right triangle to one side of the square. The hypotenuse should be the same length as the side of the square. Okay, so I'm going to pick this top side. They just said, attach it to one side here. But we're going to attach a right isosceles triangle such that this side of the square here is going to be the hypotenuse. So it might look something like this, where there's the right angle, there's a right triangle. These two would match. It's right isosceles, and the hypotenuse is attached to the square. See? Okay, next step, attach a square to each leg of the triangle. The sides of the square should be the same length as the legs of the triangle. So remember, these two sides that match were the legs. So they're saying take the side length here and make this into a square. Same here. Take this side length, make it into a square. Okay, I've gone through all these steps once. Okay, so that would be stage 1. But I want to do stage 3 yet. Okay, so I'm going to have to repeat the steps again. Okay, now when I go to repeat my steps on this one, the draw a square really is what got things started. So you're really going to jump right in here again. You see, I've already got my squares drawn from where it said draw a square. So now again, I'm going to attach my right isosceles triangles, where this is going to become my hypotenuse. So I attach a triangle there. I attach a triangle to this one as well. So I did that part. And then remember, the next part was to attach squares again. So if I attach a square here, here, there, and here. Now I've gone through the steps twice now. So this would now be stage 2. Okay, I'm still not done though. They wanted me to do, remember, stage 3 yet. Okay, so I still have to go one more through this set of steps one more time, through the iteration process one more time. So I would take each of my 4 squares here, and again I would attach the hypotenuse of right isosceles triangles. So triangle, 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 triangle. And don't forget then, for the last part here, to attach the squares. So now I'd attach a square to each of these legs. So I'd have 1, 2, 3, 4, 5, 6, 7, and 8 squares to attach there. And this finally, since I've gone through the steps not 1, not 2, but 3 times, means I have now completed stage 3. Okay? So when they specify they want stage 3, you should stop right there. Okay? If you do any more than that, it'd be incorrect. If you did any less than this, that would be incorrect. Okay? So it is important that when we do these problems, I want you to be able to recognize the correct place to stop in order to complete whatever stage is necessary. Okay, so there's a stage 3. Notice that as this fractal developed, each of the squares continued to get smaller and smaller, as well as the triangles. Okay, and as a whole, I just want you to notice too that doesn't this look like something maybe familiar in your everyday life? I mean, it looks like a tree, for example. There's your tree trunk and the branches that spread out. Or you could even look at that in terms of like our own bodies. We have veins running through our bodies, and those veins branch off, or even like a great example of that is in your lungs. The tubes that provide the oxygen in your lungs look like this, only upside down version where the air is coming in here and spreading out through your lungs. Okay, so fractals occur in our everyday lives. A lot of things in nature abide by fractals because, a lot of the things that are created in nature are are made to look complex, but they have maybe a small, simple set of rules that they just follow and repeat over and over again to create those shapes. Let's try a few more here yet, too. Some more fractals. One of the types of fractals that I want to do next is what is called a Sierpinski triangle. Okay, fractals are often named after the people that discover them. One of the first fractals ever discovered was discovered by a mathematician by the name of Mandelbrot. So if you look up on the internet, there's a Mandelbrot fractal that, if you ask me, it kind of looks like if you were to spill a bunch of ink on the floor, and it starts out with a big blotch, and then there's little blotches attached to it, and so on. But that's what it reminds me of if you were to spill some kind of liquid like ink or something onto the floor. All right, but this one's called a Sierpinski triangle. See here if I can give you a correct spelling. Sierpinski. Okay, and I'm not going to write out the iteration process. It'll take awfully long to do that. I'll just verbally explain the process that we're going to go through on this one. For a Sierpinski triangle, we start out originally with an equilateral triangle. So let's say there's my equilateral triangle. Okay, and one of the first steps of the iteration process then is to take that equilateral triangle and find the midpoint of each of the sides. So, I'm going to approximate here, but I'd say the middle of this one's about right there. The middle of that side is probably about right in there. And the middle of this side down here looks like it'd be about right in there. After finding all three midpoints, you then join those midpoints together. As you can see, it makes a triangle here in the center, as well as more triangles here, here, and here. Okay, but after you've joined all three of those midpoints, the last thing that is in the iteration process for this is for you to shade in one of those triangles. In fact, it's that one right in the center. So the center triangle here, we're just going to shade in that triangle. Okay, now they would specify in the iteration process to then repeat these steps, but only do so in the unshaded triangles. So this would be stage 1 of a Sierpinski triangle. Okay, so for example, if I wanted you to go to, let's say, stage 4. Okay. Actually, not 4, because I want to use that for your homework. Let's say I wanted you to go to then stage 3. Let's go to stage 3 then. Okay, that's stage 1. So like I said, you only repeat the process in the unshaded triangles. So up here in this unshaded triangle, I would find the midpoint of all three sides. I would connect those midpoints, and I would shade in only the middle triangle. Okay, but that's not enough for stage 2. I still have to do that same thing I did there, both here and here. So again, I would find midpoints, midpoint, 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 connect them, and shade that in. Same here, midpoint, 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 connect them, and shade it in. That finally would be stage 2. Okay, again, if I'm going to repeat those steps, I'm only going to do that in the unshaded triangles. So I got to go one more yet if I want to do stage 3. So stage 3, I hope you now figured out, would then create even smaller triangles, but they would be located here, 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 and there. See how I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles that haven't been shaded in? So we would do that, these steps again, in each of those. So you'd have a little triangle there that would be shaded in, a little triangle here that gets shaded in, a little triangle here that gets shaded in, a little triangle there, a little triangle here, little triangle there, little triangle here, little triangle there, little triangle there. And all those get shaded in. That finally would be stage 3. Okay, you can kind of see it in the shaded in triangles as well. We had one big one here. That was stage 1. Stage 2 had these medium-sized ones here, here, and here. And then stage 3 had the even smaller ones surrounding those. Here, here, and there. Okay, so that's a Sierpinski triangle. On a related idea, I want to show you what's called Pascal's triangle. Okay, so you may or may not, I don't know, maybe you've heard of Pascal's triangle. It's actually used for coefficients, for when you have to multiply different polynomials. So it may be something you've seen before, but Sierpinski, as you can tell, he's probably like Polish or Russian, you know. Pascal, I believe that's French. So these are two totally different mathematicians that, lived in different parts of the world. Okay, but I wanted to show you something here, though. With Pascal's triangle, this is like a numerical version of a fractal. We're going to repeat steps over and over again on this, but it's going to involve some numbers on this one. So Pascal's triangle starts out like this. We start with just a triangular shape of ones. Okay, and in order to, and we're going to broaden out this triangle yet. But in order to do so, what I want you to do is, the pattern is this, the iteration process is this. You just add together these two numbers, and then these two numbers, as you can see, add up to 2. So whatever the sum is, you put right in between the two numbers right below it. So 1 plus 1 is 2, and then after that, you always put 1s out on the edges. So you always put 1s on the edges. So look, 2 plus 1 would be 3. So I'm going to put a 3 there. 2 plus 1 again is 3 again, and then I put a 1 and a 1. Okay, see it? 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. And then we put a 1 and a 1. Okay, 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 5, or 4 plus 1, 5. Put your 1s on the outside. Okay, I want to keep going with this. I want to do 2 more rows of this, and then I'll show you something that happens here. So 1 plus 5, 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1 is 6. 1, 1. Okay, do 1 more row of these, and then I'll be able to show you what happens. 1 plus 6, 7. 6 plus 15, 21. 15 plus 20, 35. 20 plus 15, 35. 15 plus 6, 21. 6 plus 1, 7. And don't forget your 1s on the ends. All right, so you see how you can keep doing this forever? Okay, and if you wanted, you could keep going with Pascal's triangle. But at this point, if I stop here, I want to now look at Pascal's triangle from a slightly different view. Okay, instead of looking at it as 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on, I want to focus on the odds versus the evens on the numbers up here. In fact, what I'm going to do up here is I'm going to cross out all the odd numbers. So, 1 is an odd number. two's even, so I'm going to circle the evens. So I'm going to cross out the odds and circle the evens. So odd, 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 even, 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 odd, 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 even, even, odd, 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 even, odd, even, odd, even, odd, 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 odd. All right, so after crossing out the odds and circling the evens, you may recognize a familiar pattern. Okay, look at your ones that are crossed out versus the ones that are circled. In fact, if it helps you see it a little better, see how I have all these circled here in the middle? Notice all these circled ones form a triangle shape there. And then each of these evens as well, I'm going to, instead of circling them, I'm going to change them into triangular shapes as well. Triangle, triangle, triangle. And after doing that, now I hope it's obvious. Remember the Sierpinski triangle we just did? Where we had the overall triangle shape. We found the midpoints, we shaded in the middle triangle, and then we repeated the process in the open triangles. Okay, if you look, the way this is drawn up right now, odds versus evens, that's a stage 2 Sierpinski triangle. There's the big triangle here in the middle, and then the smaller ones surrounding it here. So that'd be a stage 2. If you want to see a stage 3 Sierpinski triangle, you'd have to continue on with Pascal's triangle and go down quite a bit further. You know, that's why I stopped here, but if you keep going with this, you can actually create stage 3, stage 4, stage 5, and so on of a Sierpinski triangle. So it turns out the two are related, Pascal's triangle and Sierpinski's triangle, and even though they were discovered by two totally different mathematicians at different parts of the world. Okay, but somebody with a lot of time on their hand apparently discovered that if you look at odds versus evens on Pascal's, it actually is a Sierpinski triangle. Okay, fractals, as I said, occur in nature, and of course they're man-made as well. I wanted to take my laptop here, and if I could get this up here close enough and show you, these are all examples of fractals that I just put in a simple web search for fractals. And as I was mentioning earlier, see the tree shape there? That's created by doing fractals. There's all kinds of interesting patterns though, kind of like I said earlier, psychedelic looking shapes and stuff. These are all fractals and shapes that were created simply by putting in equations into a computer, and the computer generated the shapes by inserting the equation into itself. So that's what you can do. You can take a math equation, insert the equation into the equation, and it produces shapes like these. Okay, one of the common shapes in nature that is a fractal is like this spiral shape here. Okay, spiral shapes occur a lot in nature. That, it looked like right there, looks like different sections of a nautilus, the seashell shape, the nautilus. Okay, but spiral shapes also occur. I don't know if you've ever looked closely at a sunflower. The seeds in a sunflower work their way out in a spiral. Just your basic evergreen trees, they have cones, that they drop down. And if you look at the cones, when they're shut, the different tines or the spikes that stick out on that cone, when it's closed, they form a spiral pattern, and then as it opens up, you don't happen to see the spiral as obvious. Okay, but if you catch a cone when it's those cones when they're closed up before they open up and drop off the tree, you'll see that same spiral pattern. In fact, let's try another fractal here that will result in, like I was mentioning, that spiral pattern. Okay, so on this one, again, I'm not going to write all the iteration process up here. It takes too much time for me to write the steps. I'll just kind of verbally explain it to you, and you'll start to catch on, I assume, to the pattern here. But again, I'm going to start off with an equilateral triangle. Okay, but this time I'm going to find the midpoint again. I'm going to find the middle of each side. Okay, but this time, instead of connecting the midpoints and shading it in the middle like we did with the Sierpinski triangle, this time I'm going to do this. Okay, after finding a midpoint on a side, what I'm going to do is, see that distance from here to here that's half of the full length? I'm going to use that as one side of a new equilateral triangle that I'm going to attach here, like that. In fact, instead of doing the midpoint of all three sides, I'm just going to do the midpoint of this one side. Okay, and that's already stage one right there. Okay, I found the midpoint of one side, and then I attached a triangle with that side length equal to that half right there. With side lengths equal to that, I attached that triangle right there. So there's stage one. Now if I were to repeat that process now on this side of the triangle now, where I find again half of it, split it in half, and then use that half to create a new equilateral triangle like that, that would then be stage two. Okay, do you see where I'm going with this? Okay, on that triangle now, see this side right here? I'm curling my way. See this? I'm curling my way in. So I find half of that side, make that half into an equilateral triangle. There now is stage three. Okay, if I were to keep going with this, do you see? I'd find half of that side right there, make it into a triangle. Okay, there would be now stage four. Okay, and it's forming that spiral shape. You see it? Started out as a big triangle, and they keep shrinking as they go around like this, and they would just keep curling around and around and around and spiraling forever. You know, it would get so small eventually that, you know, the width of my marker wouldn't be able to actually even draw the triangles. But theoretically, you know, if you were, if these lines were not to have any thickness whatsoever, but theoretically you could keep going on forever like that and keep spiraling down in further and further in there. Okay. Now there's one last fractal I want to get you started on, because it's like the Sierpinski triangle. It's going to be part of your homework. Okay. And this one initially started out as what's called Koch's curve. Koch's curve. And it's ironic, and that's pronounced Koch, by the way. But it's ironic that it's called a curve because it actually doesn't have any curves in it. Okay, but it starts out like this. You start out with a segment, and the very first thing that you have to do is trisect the segment, not bisect. Remember, bisect means to cut into two equal pieces, but instead, I want you to trisect this. So in other words, we're going to cut it into three equal pieces. Okay? So for example, if this, you know, theoretically had a length of 9, let's say, you would then split this into 3, 3, and 3. Okay? Now, after trisecting it, the next step in the iteration process is to eliminate the middle section of this. You know how I have 3, 3, 3? I'm going to eliminate that. And instead, I'm going to replace that now with 2 more 3 sections that I'm going to lean up against each other. So that's 3 and that's 3, see? So you might say that, and this would be, by the way, stage 1. That would be stage 1. So you might say in the long run, what I did really was, after trisecting it, it sprouted a spike in the middle. It grew a spike right in the middle. Okay, you would repeat this process then with any and all segments that are left now. So for stage 2, I would have to take this 3 and trisect it. So I would split it into 1, 1, and 1, and again grow a spike in the middle. That's 1 and 1 as well. So I would do that here. I would do that here. I would do that here. And I would do that here. So there is stage 2 of a Koch's curve. Again, no curves in it. Okay. If you ask me, it kind of looks like barbed wire. That looks like something you wouldn't run into and tear your skin up or something if it was on a fence, like that razor wire. Now, we're going to do a variation of this for your homework assignment. You're going to be doing a stage 2 Koch's, not curve, but this one is going to be called Koch's snowflake. Okay, and yes, it's going to look like a snowflake in the end, because if you do this now, not just once like this, but if you were to repeat all these steps we did like that for 2 more sides of a triangle. So again, if you were to sprout one big spike in the middle like we did there, and sprout one big spike in the middle here. Okay, and then I'd have to do the smaller ones as well if I wanted to do stage 2. So you'd have a smaller spike there, smaller spike there, 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 and there. And of course, erase all that stuff. So you can see then, as we did that, not just along here, but along there and along there, it starts to look like a snowflake. Okay, so that would be a stage 2 Koch's snowflake. There's a picture of this in your textbook as well, on page 381 at the very top of that page, 381. It would be the 3rd picture going left to right. It's the 3rd picture over. It would be also another picture of a stage 2 Koch's snowflake. Okay, so that's part of your homework, a stage 2 Koch's snowflake. And I also want you, for your homework, to draw a stage 4 Sierpinski triangle. Okay, and again, make sure you go just the right amount of steps. Stage 2 means you go through the steps twice. Stage 4 means you'd have to go through the steps 4 times. Okay, so that's part of the problem. I want to make sure you understand exactly where to stop. Okay. If you have any more questions though about fractals, let me know. Get a hold of me, and you can text me through Remind. You can send me emails. But that should be enough to prepare you to do your homework, which I said was those 2 fractals. See ya on our next episode.